When people see the Grand Canyon for the first time, it tends to elicit a breathtaking, "Whoa." But if you've seen it for yourself, you know that while the mile-deep red rocks are pretty, the real beauty sets in later, when you look out at its grandeur and try to visualize the millions of years of erosion happening at once. That's when you really start to appreciate it. But it's hard to appreciate what you don't understand. So when most people look out at a vast industrial complex, they don't go from whoa to wow. They go from whoa to you. I'm not here to tell you that we need oil and gas in our future energy mix. I'm not here to relentlessly point out that nearly all of the world's materials start out as petrochemicals. Those arguments, while valid, miss the point. The point is that more than half of the world's emissions come from making materials, and no amount of EVs, solar panels, and windmills can fix that. You don't have to know all of the ins and outs of chemical and material production to develop an intuition for why this is the case. But you do need to follow my train of thought. So let's start with a visual you can remember. There are 3 elements to this picture. 1. White smoke-looking stuff spewing into the sky. 2. Industrial equipment made of steel. And 3. A beautiful sunset. Today, we only care about the white smoke-looking stuff spewing into the sky. When most people see that white smoke-looking stuff, they tend to assume that those are the dreaded carbon emissions. And in a sense, they're right. But technically, they're mistaking the symptom, water vapor emissions, for the disease, heat-driven energy-intensive processes. Go back and look at that photo. Do all of those water vapor emissions look the same to you? There's a fundamental difference between the wispy, cloud-like water vapor emissions close to the ground and the intense, billowing white cloud in the center of the photo. Understanding that difference can teach us a lot. The wispy white clouds are produced when we need to cool stuff, and the intense, billowing clouds are produced when we need to heat stuff. When you need to cool something at a plant, this is usually how you do it. Cooling water from some large body is pumped to the site from a public utility. That cooling water is then sent to heat exchangers throughout the plant. In those heat exchangers, the hot stuff cools by making the cooling water hot. Okay, so the cooling part is done, but now our cooling water is hot. We can either dump that now hot water into the environment, that's called thermal pollution, or we can spray it into a cooling tower and use fans or natural convection to remove heat via evaporation. Some of that water condenses again and is recycled, but some doesn't, and that's where those wispy white clouds come from. Conversely, when you need to heat something at a plant, this is usually how you do it. A hydrocarbon, like natural gas, is combusted to produce heat. Doing that also produces CO2, water, NOx, SOx, and some particulates. That generated heat is either applied directly, like in a furnace, or it's applied indirectly, like in a boiler, which makes steam, which is transported across the plant to heat stuff. Either way, now you have the heat you wanted, but you still need to deal with the CO2, water, NOx, SOx, and particulates. Since the NOx, SOx, and particulates are extra bad, we get those out via filters and specialized processes. But we emit the CO2 and water out the smokestack, and that's where water forms the intense billowing white cloud in the center of that photo. And it's also where the CO2 escapes invisibly. Those visible emissions hide the invisible problem. Making chemicals and materials requires a lot of energy, and we transfer that energy with hydrocarbon-derived heat. It's usually not the flare, unless something has gone horribly wrong, or CO2 directly produced by the reaction. Cement is the classic exception. But to understand why this is the case, you need to get familiar with those energy requirements. And to do that, we're going to use a basic model called the oxidation ladder. It's not perfectly accurate, but the goal isn't to use the model for techno-economic analysis. The goal is to develop intuition. It goes something like this. If we want to make stuff, we need to make it out of something else. And when we look around at our environment, we're limited to stuff we find deep underground, like crude oil, stuff we find at the surface, like sand, stuff that grows on the surface, like trees, stuff that's in the air, nitrogen, oxygen, and argon. Excluding the stuff that grows on the surface, everything in our environment has been there for a very long time. And like anything, if you give it enough time, it will reach a state of stability, an equilibrium. But equilibriums depend on temperature, pressure, and the existence of other stuff. Take Earth's surface, for example. The temperature averages out to around 60 degrees F. Pressure is 1 atmosphere, and there's a lot of oxygen around. So, as time passes in this oxygen-rich environment, stuff on or near Earth's surface is oxidized, and stuff deep underground is reduced. And since everything humans do happens on Earth's surface, the degree to which a molecule is reduced turns out to be a good proxy for how much energy that molecule can release. This should be intuitive. We know that once we get something burning, it tends to burn until it's all burnt. For example, we know that wood will continue to burn in air and release energy, in the form of heat, as long as we give it enough energy to get started, perhaps with a match or lighter. Fossil fuels like crude oil and natural gas work the same way. They're just less oxidized than wood, so they have more energy to release. But while most reactions need at least a little energy to get started, we'll have to talk about kinetics another time. Not all reactions release energy as they proceed. Some reactions will only proceed if you continue to provide energy. We usually try to avoid those energy-consuming reactions because energy costs money. But if A, feedstocks are super cheap, or B, the chemicals and materials you can make from those feedstocks are super valuable, we'll do the energy-consuming reactions anyways, like converting ethane into ethylene. So what can we do about it? Can we avoid those reactions? Can we reduce the energy requirements? Can we get the energy we need from something other than heat? We have the answers to those questions, and they tell us that we really only have 5 solutions to the issue at hand. Capture the CO2 that you produce. Produce heat by burning something that doesn't produce CO2. Produce heat with renewable electricity. Drive the reaction with renewable electricity. Do a different reaction. Each of those solutions deserves its own post, or series, so we'll have to talk about them later. All I'm really trying to impress upon you now is that this is mostly an energy problem, and it's not as simple as attaching some windmills and solar panels to a chemical plant. It's also not as simple as innovation in catalysis or infinite heat integration. And it will, unfortunately, never be as simple as choosing the best technology. We simply can't ignore factors like urgency, politics, and financial markets and still expect the best technology to prevail. Think about it. Sometimes demand for one product produces byproducts, subsidizing the cost of those byproducts, making them look like co-products. Sometimes we accidentally build an entire global economy on that subsidized basis and are left with trillions of dollars worth of assets and infrastructure. And sometimes companies have to compete for capital in a highly competitive environment where investing in bits delivers higher and faster returns than investing in atoms. Solving this problem starts with effective communication that encourages realistic capital and resource allocation. The bottom line is that people need to know where stuff comes from, why we make it the way we do, and what we can do about it. If policymakers and investors fail to grasp those concepts, we'll end up deploying capital inefficiently and building more moats to progress.